Welcome, curious minds, to another deep dive. Have you ever, paused to wonder what's really happening inside your laptop or smartphone? When you tap an icon or type a message.
Or even just watch a video, yeah.
Exactly. We're diving into the very heart of these machines today, the fundamental thinking part of every digital device.
We are? We're talking about the central processing unit, the CPU.
That's the one.
It's often called the brain of the computer,
Yeah.
right? And, well, analogies always have their limits, but it's a pretty good starting point for understanding how these incredible devices actually function. We've gathered some really fascinating articles and research notes for this session. Our mission really is to peel back the layers, understand its core components,
Let's see how it works.
and reveal the surprisingly elegant yet incredibly powerful process that drives, well, everything you do digitally.
Okay, I'm ready. Get ready for some genuine aha moments as we uncover not just what the CPU is, but how it orchestrates billions of operations every single second. Right there on your desk or, in your pocket.
Billions is the key word there.
So let's unpack that. Our sources call the CPU arguably the most important component of a computer. Why? What's it actually doing at that fundamental level, even if the brain analogy isn't perfect?
Well, at its most basic level, the CPU processes instructions.
Right.
That's its job. Every single action your computer takes, opening a file, rendering a complex graphic, it all breaks down into countless, tiny, simple instructions.
Okay.
And the CPU is the engine executing them. Now, here's something crucial to grasp. Unlike a human brain, which can juggle lots of things in parallel, a single CPU core typically runs one simple instruction at a time.
One at a time, really.
One at a time. The real magic, the reason our complex digital world even works, is its breathtaking speed. It carries out billions of these simple instructions every single second.
Wow. So that seamless multitasking we think we see on our phones or laptops, it's basically an illusion created by just raw, relentless speed.
Pretty much.
Ah.
Billions of tiny, precise, sequential steps, one after another, happening incredibly fast.
That's fascinating. It makes you wonder, though, has it always worked this way? Or did we have to, invent this whole approach?
That's a great question, because the way CPUs function today is really a testament to a revolutionary idea. Before about 1943, early computers, they could store the data they worked on, sure, but the program itself, the instructions, that wasn't stored in the same way. Instructions often had to be input one at a time, manually. Think switches or punch cards.
Oh, wow. So, rewiring the machine for every different task?
Essentially, yes. Imagine that. Then, around 1943-44, the brilliant mathematician John von Neumann and his colleagues, they introduced this game-changing concept, storing the program instructions right alongside the data in the computer's main memory.
Oh, okay.
And this gave birth to the stored program computer, what we now call the von Neumann architecture. Both instructions and data reside in the same main memory. Think RAM, mostly, and the CPU just fetches both from there as needed.
It's actually hard to overstate how huge that was. Before von Neumann, changing a computer's program literally meant physically changing its wiring.
Exactly.
Storing instructions like data meant computers became truly programmable. General purpose. It wasn't just a hardware tweak, it was kind of the birth of software as we know it, wasn't it?
It absolutely was. It enabled everything from spreadsheets to streaming video, all because the CPU could now dynamically fetch its own instructions from memory.
Okay, so the CPU is this incredibly fast instruction processing hub. How is it actually built, though? What are the specialized units inside that let it do all this stuff so efficiently?
Right, so inside the CPU, it's like a miniature city. Lots of specialized units working together. Two of the most critical ones are the control unit, or CU, and the Arithmetic Logic Unit, the ALU.
CU and ALU. Got it.
Think of the control unit, the CU, as the orchestra conductor. It doesn't play the instruments itself,
Right.
But it coordinates and controls all the activities happening inside the CPU. It fetches instructions, decodes them, figures out what they mean, and then sends out timing and control signals.
Tells everyone else what to do and when.
Precisely. Tells the other components how and when to execute those commands. It keeps everything synchronized, like a metronome, ensuring perfect timing for billions of operations a second.
Okay, so if the control unit is the conductor, what's the Arithmetic Logic Unit, ALU, doing? Is that where the actual heavy lifting happens? That playing the notes?
That's it exactly. The ALU is where the real work gets done. This is where all the arithmetic operations you're adding, subtracting, multiplying, dividing are executed.
A math part.
The math part, yeah. But it's not just a calculator. It also carries out logical operations. Things like checking if one value is less than or greater than or equal to another, or performing logical AND or NOT operations.
Ah, so it makes decisions too, based on logic.
Exactly. It's not just crunching numbers, it's making fundamental comparisons and decisions based on the logic embedded in the instructions.
That's a lot of intricate steps happening incredibly fast. But, to do all that work efficiently, the CPU must need its own super fast internal memory, right? What about its immediate workspace? Our sources mention registers and cache. How do they fit in?
You're absolutely right to bring those up. They're crucial. Registers and cache are both types of memory, but they're incredibly fast and specialized, living right there inside the CPU chip itself.
Okay, faster than normal RAM.
Oh, much, much faster. Registers. Think of them as tiny, like super fast scratch pads. Just a handful of storage locations the CPU uses to temporarily hold data it needs right now for an instruction, or the immediate result of an instruction it just performed.
So the absolute fastest memory it has.
Fastest memory available, yes. Crucial for its immediate active operations. Then you have cache memory. Also on the CPU chip, it's a bit larger and a tad slower than registers, but still vastly faster than main RAM. It acts as a high-speed buffer.
Yep.
It holds regularly used data and instructions, kind of anticipating what the CPU will need next to speed up access and avoid going out to the slower main memory all the time.
Okay, that makes sense. It sounds like those registers are absolutely vital then, constantly being accessed and updated. Let's dive a bit deeper into those because they seem key to tracking all this lightning-fast work. What are the main players? The ones that make this whole dance possible?
Yeah, they really are central. Our sources highlight 4 critical registers in this von Neumann architecture. Each one has a very specific, vital role in managing the flow.
Okay.
First, the program counter, or PC. This one's like the stage manager holding the script. It holds the memory address of the next instruction that needs to be fetched and executed, always looking ahead.
Got it. Next instruction's address. What else?
Then there's the memory address register, the MAR. This is the CPU's pointer, you could say.
Yeah.
It holds the specific memory address that the CPU wants to read from or write to right now. Could be an instructions address, could be data's address.
So where in memory to look?
Exactly. And paired with that is the memory data register, the MDR. This is like the temporary holding bay, or maybe a loading dock. It holds the actual instruction or the actual data that has just been fetched from that memory address the MAR pointed to.
Ah, okay.
Or it holds the data that's about to be written to the memory address in the MAR. It's the go-between for data moving between the CPU and memory.
Okay, PC for next instruction address, MAR for current target address, MDR for the actual date instruction going back and forth. What's the last one?
The last key one is the accumulator, or ACC. Think of this as the CPU's primary workspace for calculation results. It temporarily holds the intermediate and final results coming out of the Arithmetic Logic Unit, the ALU, after an instruction is executed.
So the ALU does the math, the result lands in the accumulator.
Precisely. Before that result is potentially sent back out to main memory via the MDR and MAR.
Right, so the MAR knows where to look in memory, the MDR carries the stuff. They definitely work hand in glove, like a really efficient, super fast courier service just for the CPU.
That's a good way to put it.
Okay, now this is where it gets really interesting, I think. You see how all these pieces, the CU, ALU, all these registers actually work together. The CPU operates by constantly repeating what's called the fetch-decode-execute cycle. So what are these 3 fundamental operations? What's this rhythm?
This cycle is, it is the CPU's heartbeat. It drives literally everything your computer does. It's simple in concept, but incredibly fast in practice.
Okay, break it down.
Sure. 3 steps. 1, FTCH. First, the CPU fetches the next instruction from main memory. It uses the program counter, PC, to know where to look, puts that address in the MAR, and pulls the instruction into the MDR.
Gets the next order.
Gets the next order, exactly.
Yep.
Decode. Then, the control unit takes that instruction from the MDR and decodes it. It figures out, okay, what am I actually being asked to do here? Is it an addition, a data move, a comparison?
Understands the order.
Right. 3, execute.
Yeah.
Finally, the instruction is executed. The control unit sends the necessary signals, often involving the ALU if it's math or logic, or maybe just moving data between registers or memory. The actual work gets done.
Performs the order. And
then it loops. Immediately back to fetch for the next instruction, whose address is already waiting in the now incremented program counter. Fetch, decode, execute. Over and over and over. Millions of times a second.
Right.
To really see it in action, let's walk through that simple example from our sources. Adding 8 and 4 and storing the result. It makes these abstract parts much more concrete.
Fantastic. Yeah, let's follow the data. So imagine the CPU starts and the program counter PC is pointing to, say, memory location 5. And the instruction there is load 8 into the accumulator.
Exactly. Let's trace it. Step 1, FTCH load 8 instruction, and then the data 8. Okay, the PC has 5. That address 5 is copied to the MAR.
Tells memory where to look.
Right. The instruction at address 5, load 8, is fetched from memory and lands in the MDR. Crucially, the PC immediately increments to 6-fit, getting ready for the next cycle.
Already pointing to the next instruction.
Already ready. Now, the control unit decodes that load 8 instruction in the MDR. It realizes, okay, I need to load data into the accumulator, and that data is the number 8. Say 8 is stored at memory address 10, so 10 now goes into the MA.
Pointing to the data this time.
Pointing to the data. The value 8 is fetched from memory location 10, brought into the MDR, and then the control unit directs it to be loaded into the accumulator, ACC. Phew. End of step 1, the ACC now holds 8.
Okay, ACC has 8, PC is pointing to 6. What's next?
Step 2, fetch, decode, and execute add 4.
Right.
The PC, now at 6, points to the next instruction. Let's say it's add 4. So address 6 goes to the MDR.
To instruction.
Fetch the add 4 instruction into the MDR. The PC increments again, now it's at 7. The control unit decodes add 4. It signals the ALU. It says take the value 4, maybe 4 was part of the instruction itself. Or maybe it fetches it from another register or memory location, depends on the exact instruction, and add it to the value currently in the ACC.
Which is 8.
Which is 8. The ALU performs the addition. 8 plus 4 equals 12. That result 12 is put back into the accumulator, ACC. So now ACC holds 12.
Got it. Addition done, PC is at 7. Last step.
Step 3, fetch, decode, and execute store result.
Exactly.
Exactly. The PC, at 7, points to the final instruction for this little task. Store the result in memory location 11. Address 7 goes to the MAR.
Fetch the store command.
Fetch the store instruction into the MDR. PC increments one last time for this sequence. The control unit decodes store. It executes it by taking the value 12 from the ACC and putting it into the MDR. Then it puts the target address 11 into the MAR.
Tell memory where to put the data.
And finally, the control unit signals memory to write the value 12, currently in the MDR, into memory location 11. Job done.
And just like that. Wow, a simple addition is complete. But it took this incredibly intricate ballet of registers, the ALU, the control unit, all perfectly timed by that fetch, decode, execute cycle.
Billions of times a second.
It's happening so fast we don't perceive any of those individual steps. But they're all there, meticulously coordinated. It really makes you appreciate just the ingenuity of it all.
It really does.
What an incredible journey inside the heart of our computers. We've peeled back the layers to understand that your CPU, the central processing unit, it really is the core processor, handling billions of instructions a second through this surprisingly simple sequential process. It's the absolute unsung hero.
It is, and we've seen how that foundational idea from von Neumann, storing the program instructions right along with the data, totally revolutionized computing. It paved the way for everything we do with computers today.
Yeah, the birth of software, really.
And we explored those key internal parts, the control unit as a conductor, the arithmetic logic unit doing the actual work, and those vital registers like the program counter, MAR, MBR, and accumulator. They all come alive during that constant, relentless fetch, decode, execute cycle.
Knowing all this, I mean, the next time you just open an app or browse the web, you can't help but have a much deeper appreciation for these complex, yet somehow elegantly simple processes happening at lightning speed right under your fingertips.
Absolutely. It's not magic, is it? It's just meticulously designed architecture working incredibly fast.
Powering our entire digital lives.
And, this understanding, it really reveals the genius behind modern computing. But it also raises a fascinating question, I think. When we talk about really complex stuff like AI or sophisticated simulations, what does it truly mean for a machine to process information or even think when fundamentally it's just following billions and billions of these very simple, precise steps every single second?
From predicting the weather to just, recognizing your face on your phone.
Yeah.
It all comes down to that cycle.
It all comes down to that cycle. Executed at incredible speed, it's definitely a question that keeps on giving.